Before we begin, I'd like to invite our Dean of Engineering, Professor Yossi Rosenwaks, to say a few words.
Good morning. I'm also from electrical engineering, but from the other side. And there is another big conference in the campus, so Nano Israel. So I apologize that I have to leave right after my blessing. So it's a great pleasure to be here again and congratulate Meir. As you know, Meir just recently celebrated 50 or 60? 60. And it was really an impressive conference. And again, impressive list of speakers today. And many people will come during the day. So I'll be back to the prize ceremony. I wish you a very enjoyable and successful day. And thank you again, Meir, and your family for supporting this and supporting other activities in the faculty and in the university, on which probably the president will talk during the ceremony. So thank you very much, and thank you for coming.
All right, so we can begin. Our first speaker is Professor János Körner from Sapienza University in Italy, and he's going to talk about codes beyond greed and random choice.
All right, so let me try to. So it works. Okay. Okay, so I'd like to thank the organizers for inviting me. It's a great honor to be here. I feel very close to this country in many ways for obvious reasons. Okay, even though, well, now I'm in Rome, actually. Okay, so I would like to talk to you about something that maybe is an intersection of so many things that hardly anybody would be interested, but I will try my best. Okay, so what I would like to talk about is, why, my negative experience with trying to get ahead in what is sometimes called multi-user information theory. And so that's a field of exploiting the limits, the theoretical limits of communication through small networks of information sources and noisy channels. And in the late 70s, I gradually came to realize that there are, very serious obstacles in generalizing what people have done had done in that time. So generalizing this to larger networks involving more sources and more channels. And I like to talk about these stumbling blocks because I feel that we have still not overcome those difficulties. And the reason why we have not is that we are lacking general techniques, general methods, either to, construct good codes or also to get, limitations of what you cannot do anymore. So-called converse results. And I'll try to give you a feeling for why that is and what should be done to get ahead. Okay? So maybe some of what I will tell you is already known because I myself have talked about it, and so did some others. But the rest will be new results of mine, and it's there that maybe nobody will be interested, but I still try to convince you that those are things that are, in some very broad sense, information theory. But it's certainly combinatorics. Okay, so let me see why this doesn't seem to go ahead. So, I mean, these arrows don't seem to work.
Really? That's strange. Just try that. Interesting.
It did work before.
It worked just a second ago, yeah. Which do you have technical support here? Which computer is this on? This one, right? זה המחשב הזה? זה נראה שזה... כן, אבל זה המחשב שלו עצמו לא עובד. כן עובד.
Okay. All right. Okay. I'm sorry. All right. So, when you look at constructions in classical Shannon theory or multi-user information theory, which is part of, then those constructions practically always use either greedy algorithms, even though that's not the name that is used in Shannon theory, or random choice, which now information theory you would call random coding, but it's just random choice. And it seems to me that they have essentially the same power. They essentially give the same results in terms of constructions, that you can use them alternatively. But both of them fail in those cases that I consider stumbling blocks, and that we did discover as stumbling blocks, mostly with Scotty Martin, and that still are, the way they were back then. And that's because we don't have really alternative general construction methods. We just know some little cases where you can see that those techniques don't work. And so I feel that what is needed is codes that have more structure. And that, at least in my interpretation, means that more combinatorics is needed. Okay, so I will give you a first example that I really like, and it's really a very old problem that goes back to like mid-50s, Peter Elias's work, but I like to present this problem in what I like to call its naked beauty. I think that it's really sort of negative that, in some ways it's negative at least, that problems are presented usually within one technical field with all the technical ornamental words of that field, which then has the effect that nobody from those other fields where the very same problem rises would care. And this actually did happen to this little problem. So, at one point, Gabor Simonyi and myself, we started to call this special case. This is the simplest special case of several very interesting and extremely well-known problems. And the simplest special case that is unsolved. And this I like to call the difference problem. So what is it? You have a ternary alphabet. And then if you have a ternary alphabet, you would say that you use some block length, say n, and then you would say that 3 sequences over this ternary alphabet are different if they differ somewhere in the very same coordinate. So that is that in that coordinate, say I, you would have the 3 different symbols of your alphabet appear in that coordinate. All right? So I guess you can ask questions if something is not clear. I hope that's permitted. Okay, and then I would say that the whole set of sequences is different if any 3 of the distinct strings from this set are also different. Okay? So that's playing with the words, but difference is a binary relation, and now here you have a ternary relation. And that blows up things, that makes things extremely difficult for all kinds of reasons. And now, so if you look at this as a coding problem, then what you are interested in is fixing n, how large the cardinality of such a set of different sequences can be. Okay? And since this is very hard, you would like to evaluate it at least in an asymptotic sense. Now, I wrote here limit superior. You are not used to this in simpler problems in Shannon theory, because there you have that the quantity, this T of n, is super multiplicative, and therefore, if you normalize it the right way, then it has a limit that, at least in Hungary, which is my home country, is called Fekete's theorem. Okay, for Fekete, who went from Budapest, I guess, to Israel. Okay. All right. So because, and the reason why, I mean, here you do not have, because you have this ternary relation, you do not have super multiplicativity, because if you have a good construction and then you would try to use the Cartesian powers to get larger constructions and some asymptotic bound, I mean, that won't work, because the Cartesian powers of good constructions are not good constructions anymore. So I just write limit superior. And this is like getting from 2 to 3. It's a very seemingly, conceptually, extremely simple problem. It's still unsolved. And why is this unsolved? Well, okay, so let me just give you some feeling for what is true here. I mean, so very trivially, you can show, and I will show it to you, that you have this upper bound. So, the factor by which this cardinality grows is not more than 3/2. And this is extremely elementary, but maybe it makes you feel good if there is something that has to be proved, and that I can show it to you. Now, so you have say you have a construction, say you have an optimal construction. So the first element in your strings is either 0, 1, or 2. So there is an error there. I really meant to write 2. I'm sorry. So the third group, you have 2s, okay? So every sequence starts with either 0, 1, or 2. Now, if you just group together, so what you do, you have these 3 groups, and now you group together any 2 of them. So say you consider the strings that start either with 0 or 1. Well, these strings in some coordinates should satisfy the condition of being triferent, and it cannot be in the first coordinate. So if you put these 2 together, then you cannot get more strings than T of n minus 1. And this is true for any couple of, out of the 3 groups. And therefore, so you have for every group, this upper bound of T of n minus 1. But if you look at this, then you realize that with these 3 groups, you will have counted every string twice, which means that twice T of n is at most 3 times T of n minus 1. And that gives you this very simple-minded upper bound. So no problem there, except that I do not know of any better upper bound. Okay, so let's see the lower bound. Well, if you start to look at what you have for small block lengths, so obviously for block length 1, you can have 3, 1, 2, and those are different. For block length 2, you can see that these 4 strings give you an upper bound. I mean, give you a lower bound, so they give you a construction. But remember, you cannot do anything with these constructions, it seems, because the Cartesian powers of these constructions are not good constructions anymore. Okay, and now, well, you will see why I say you have equality. And now what's a little bit interesting is what you have for block length 4. For block length 4, you can have 9 strings, and you can see why is that, and I'll explain. And now these 9 strings have the remarkable property that they have constant Hamming distance 3. Any 2 of them have Hamming distance 3. And because of that, you can work out like a small exercise. These 9 sequences are triferent. Okay? And now, well, you can see very easily, I like this actually, why this has this property of having constant Hamming distance 3 between any 2 of the strings. Now, if you look at the first part, the first half of the strings, those are actually the 9 strings of block length 2 that there are, okay, over a ternary alphabet. Now, any 2 of these, of course, since they are different, have either Hamming distance 1 or Hamming distance 2, okay? So this divides the pairs, into two graphs that are complementary. And it just so happens that these two graphs are complementary and isomorphic. Okay? And so if you just write as a suffix, so you consider any isomorphism between this graph and its complement, and then you put next to any of the strings of length 2 its image. Well, that means that if in the first half these two strings had difference 2, Hamming distance 2, then in the second part they will have Hamming distance 1. If they had Hamming distance 1 in the first part, then they will have Hamming distance 2 in the second part, which means that any two of them have Hamming distance 3. And that immediately implies that these strings are different. Okay, so that's... and this is well known actually, especially you can make it linear. I didn't make it linear because who cares whether it's linear or not. But in its linear version, where this is also a linear code, then this is called the tetracode, and it's well known in information theory. Okay? Now, since if you work it out, then this trivial upper bound I gave you shows that you cannot have more than 9 strings. Okay? That shows that you have equality everywhere here. Okay? So that's basically, this is something you can do, then it becomes hard to get ahead with this problem for longer block lengths. Okay, so we have this small construction, and what can you do with this small construction? Well, in general, we know nothing, but since this condition of being different gives you the feeling that you can somehow, and this is true, you can check this, that if you randomly choose your elements, then you can have an exponential increase, and you can prove as a lower bound that at least the normalized value of t of n is in the limit at least the square root of 9/7. This is a very simple random choice argument, but it's by plain random choice. And we have nothing else. We don't have general instruments, general tools. That's one of my points. So with my longtime collaborator and friend, Kati Marton, we proved back in '88 that you can do better. And you can do better using this little tetracode. So this little tetracode, it's a code of block length 4, and it has 9 words, 9 mini-strings. Now, since in general we do not know better, we know nothing, we have nothing else than random choice, so you can apply random choice to this alphabet, to the tetracode. And miraculously, this gives you a better lower bound. Now you might wonder why the tetracode? Well, if you look at the optimal construction for small block lengths and you base your random choice on that, then the result that you get from 1, 2, 3, 4 is not monotonic. So out of these 4 little constructions, the best lower bound based on random choice is what you get here. And this means that you have more structure than in a plain random choice. But, so how can you do anything like that in general? I wouldn't know. So that's really a stumbling block, and this is still the best lower bound for this problem I know of. Well, now you would say, well, but that's a combinatorial problem. It's not information theory. On purpose, I presented it like I stressed this in its naked beauty, because actually what happened with this problem was that it was rediscovered. It was rediscovered by people in computer science because it was originally stated in the Shannon theory language. So actually I won't explain this, but it's just, for very simple reasons, it's just the zero-error capacity of a discrete memoryless channel for list size 2. So it's a finite list size. But there is no improvement if you have a list size that goes to infinity in a sub-exponential, at a sub-exponential speed. But so that is, and this is a very, so it's basically Peter Elias, and this problem of difference is exactly the zero error capacity of a discrete memberless channel, the following channel. You have an input alphabet and an output alphabet of size 3, and then you take the channel matrix, a matrix that has zeros on its diagonal, and say 1/2 off diagonal. Okay? And the zero error capacity for list size 2 of this channel is just precisely this problem, I mean, in the asymptotics. And it has very noble connections. I have no time to end here, but I like to say that there is this X conjecture of van der Waerden. You know, it used to be a conjecture for 50 years, and now it's a relatively young theorem. I mean, as a theorem, it doesn't have 50 years. Okay, but then it was rediscovered in computer science as the problem of perfect hashing. Okay, so I don't, and the solution, the lower bound that we have, has its weakness that in the end it's still based on plain random choice. Okay. Now, there are other examples of such problems I won't discuss in detail. And once again, in my work with Kati Martin, we discussed this modulo two-source network. And that also is an example where it seems that we cannot prove this. But it seems that there are no other ways than construct, I mean, something of a construction. So random choice won't give you the... Here we had the solution, but random choice doesn't seem to give you this. Now, okay, so what the main part of my talk is about, this general framework of problems where you have two huge sets, and in this special case, this is the code distance problem, so it's really nothing new, and I won't tell you anything new about it. It's just I would like you to look at the problem in this way. So you have this large blue set, which is the Hamming space for some fixed block length n, so all the binary sequences of length n, and then you have this red set that is actually smaller. It's actually a subset of the blue set. So it's the set of all the binary strings in which you have at least delta n ones. So in coding theory language, this is sequences that have Hamming weight at least delta n. So a constant part of the block length. And now you are looking in the blue set for a large set C sub n. C sub n would be an optimal set of this kind. That has the property that if you take any two different strings from this gray set, say, within the blue set, x and y, any two different strings, then their modulo 2 sum is in the red set. Okay? So that's what you are looking for. I mean, this seems somewhat unusual to present it this way, but it's trivial in the code distance problem. And in the code distance problem, if you fix the block length n and you fix the minimum distance n delta, then you are looking for the largest cardinality of a set that has the property I described before. And now if you are interested in the best asymptotics, so the asymptotics of the largest cardinality of such a set, then it is well known, and it is, from Cold War times, that many major results or breakthroughs for the time were discovered simultaneously or almost simultaneously by a Russian who in this case actually was an Armenian born in Georgia, so it's almost like being Jewish, and Ed Gilbert. Mm-hmm. Okay, and you all know this, that the limit superior of this, now I put in the logarithm because this is more information theory. And you have this lower bound. But you only have it for delta at most 1/2, because if delta is larger than 1/2, there is nothing interesting to say at this level. Then simply you cannot have exponentially many strings with this property. Okay? And there is no matching upper bound. This is really a problem in elementary coding theory that some of the brightest minds in the most abstract parts of mathematics have thought about, even Jean-Pierre Serre, who was the first Abel Prize laureate. And still, there is no matching upper bound. But and this is really very stunning. I'm not sure I'm good enough to make this vanish, disappear. Oh. Okay, sorry. Okay, so it's really very unpleasant and strange that there is no matching upper bound, and it's not known whether this is optimal. And this is very stunning, especially because this is something that you do by just the greedy algorithm. So you pick a string, then you throw away all those that are too close to this one, okay? And then you keep going until you just cannot go on anymore. Oh, now we are back into the situation that this doesn't get ahead.
Guess we're not good with technology. I don't know. It's stuck.
Okay.
Now?
Yeah.
Can you try that?
I'm not sure. No.
Doesn't work?
Okay. Oh, no, it works. It works. Okay, good. Sorry about that. So, the greedy algorithm gives you this bound, and nothing better is known. Well, at least some people did improve this Gilbert-Warshamov bound by a linear factor. So, but it doesn't really give a significant asymptotic improvement. So it's fair to say that this is still the best that is known about this problem. Now, I put this problem in the framework I chose because there are incredibly many problems that have the same format. So you have a huge blue set, whatever that is, I will give you examples, and then you have a binary operation, and you are looking for the largest cardinality of a set C sub n within this large blue set that has the property that there is some binary operation that will be typically the union, and the result of this binary operation applied to any two distinct elements from your set is in the red set. And with the Gilbert-Warshamov code distance problem, the red set was included into the blue set, but that's not necessarily the case. And in fact, the interesting problems that I would like to talk to you about are such that the blue set is, the red set is far away, it's disjoint from the blue set, and in a sense is far away from it. Okay? So, all right. Now, some of these problems are well known in extremal combinatorics, and if this is not new to you, at least I can offer you the authentic pronunciation of the last names of the authors. So there are these problems called intersection problems in graphs, and they start with Pál Erdős. And then there is this very interesting X conjecture once again. So Vera Sós and Miki Simonovic, who wrote several papers about such problems, had this very interesting conjecture that I will tell you about, which is now a theorem. So I put it in a dual form with respect to their form. That's because it makes the comparison with my problems easier. Mm-hmm. Okay, so F sub n will be just the set of all the graphs on a fixed vertex set, say the first n natural numbers. And then the binary operation will be graph union, which means that if they have the same vertex set, then the union of two graphs is just the one that has the edges of both the one and the other, all right? And now D sub n, the smaller set to the right, is the graph, the set of all graphs with the same vertex set that have at least 3 vertices without edges between them, which in other language means that the stability number or the independence number of these graphs is at least 3. Okay? And then you are interested in the largest cardinality of, of this gray set that is a subset of F sub n, such that if you take 2 different elements, 2 different graphs in that set, then their union will be a graph that has independence number at least 3. Now, okay, so like you can see, this is also a problem that lived as a conjecture for a long, long time, and then David Alice, Yuval Filmus, and Ehud Friedgut in 2012, actually just in time for an important conference, birthday conference of Vera Shosh's, they actually proved their conjecture. They actually sent an email to Vera Shosh, I guess 2 days before her birthday conference. So, okay. So, and you see, the conjecture was very natural and very nice. And the conjecture did say that here the optimal construction will have some very special form. And certainly, this very special form gives a good construction, which means that now you consider all the graphs. You could look at a graph since the edge set is, the vertex set is fixed, and you could now describe your graphs with, say, their characteristic vector, the characteristic vector of their edge sets. Now, you just consider you fix 3 vertices, and you consider all the graphs that have no edge on these 3 vertices. Now, naturally, the union of any 2 such graphs is still a graph that has this property, because none of them has an edge here, so their union won't have an edge between these 3. So that means that you consider all the graphs that have this property. That means that, for 3 pairs, you have already decided what's going to happen to them, no edge. Now, the edges can be anywhere and in any number between the rest of the vertices. So that gives you this many graphs in the family. So that's a good construction. But what is the special form that this construction has? Well, it's like if you look at the graphs as, in the form of the characteristic vectors of their edge set, then this means that you have a projection. You have a fixed projection. So you take all the objects, all the natural candidate objects that have a projection fixed. This is usually called nuclear construction or kernel construction, and what actually Szymanowicz and Shosh conjectured, and that Alice, Filmus, and Friedgut proved, was that not only is this construction optimal, but it's also unique in being optimal. So that's the only optimal construction. And they even proved something that was not conjectured, I think, by Szymanowicz and Shosh. And that is that if you now have a looser, a milder restriction, so, it's not natural in this form to say. So it means that the edges of an eventually larger odd cycle are missing, okay? Then, theoretically, this might give you a larger optimal set, and they proved that it does not. Okay? And so that's really surprising, I find. But, okay, so this is already something I told you. And so with this problem, it's, it's still true that the blue set on the right-hand side is contained in the set on the left-hand side. And this really gives you, and in these cases, it seems that very often the kernel structure is optimal. But if they are not, then, I mean, if the two sets do not have this inclusion relation, then simply the kernel structure, I mean, most of the time, the kernel structure is simply not there. So the kernel structure, if it's there, then it gives you at least a lower bound. And then they often conjecture that it gives the optimum, and very often it does. But if those two sets are disjoint, then things are completely different. And I won't tell you why and how. I came to look into several problems where where the left-hand side set is the set of Hamilton paths in a complete graph. That's really because it was natural to generalize and consider new problems in information theory, considering permutations rather than just strings from a finite alphabet. And from permutations to Hamilton paths, that's only a very small step. And somehow, when you consider Hamilton paths, then this condition on the union, often is very natural and is completely different from what you would consider as a condition on strings. Okay, so now if you consider the Hamilton paths from a fixed complete graph, okay, so you have one and you have another one, so the green one and the red one, for instance. Okay, so now here is a problem. Okay, so what happens if you have Hamilton paths from a fixed graph? Well, the union of two Hamilton paths always contains a cycle, always. Because, a Hamilton path is a spanning tree, and that's maximal with respect of not having cycles. So if you take the union of a fixed Hamilton path with any other Hamilton path, it necessarily has at least one edge that is not in the original one, and then adding that single edge to your original Hamilton path will result in a cycle somewhere. But you have no control on this cycle. Now, what if you impose the condition that you want to have the largest set, the largest cardinality set that has the property that the union of any two of its elements that are Hamilton cycles now give an odd Hamilton cycle. I will show you in a little detail just what is trivial, and then I will talk more, superficially about the rest. Okay, so now I have this paper from 2012 with Silvia Messoudi and Gabor Simonyi about this condition of having an odd cycle in the union. So it's really very simple. So the result is like this, and basically these numbers, these binomial coefficients, correspond to the number of so-called balanced bipartite complete graphs. Okay, so what is a balanced bipartite complete graph? It means that you divide the vertex set into two equal halves as much as you can. Well, if n is odd, then these are the two sizes. And now what you can see is that any Hamilton path in your fixed complete graph uniquely defines such a graph, a bipartite, complete, and balanced graph that contains it. Okay? And clearly, because this in itself is a bipartite graph, therefore the union of any two of its Hamilton paths is still a bipartite graph, so it won't contain an odd cycle. Which means that if you have a construction for our condition, then the Hamilton paths in that construction should come from different balanced bipartite complete graphs. So that just shows everything. That just shows everything. So that shows that actually, so this was the number of these balanced bipartite complete graphs for n odd and for n even, and that solves the problem very easily. Okay? Now, you can ask, what if we want not just an odd cycle, but we want a short odd cycle. So what if we want a triangle? Like in the Alice Friedgut, Filmus Friedgut problem, it didn't matter whether you, instead of an odd cycle, you put a triangle in the condition. It doesn't change the condition. Is that true for this problem too? Well, I don't really think it's true, but for for n equals 5, where we could check it by hand, it is true. So it's not clear what happens. Now, it's far less trivial when you consider the even cycle. Well, if we consider the even cycle case, then one thing you can have that's trivial is that you consider, once again, the balanced complete bipartite graph. Certainly, if you have any two, like I said before, if you consider any two Hamilton paths in that, then this will give you more or less this many Hamilton paths, and the pairwise union of any two of them will have an even cycle. That's perfectly trivial. But what's a little bit surprising is that you can do better. Now, what did I do? No. So you can do a little bit better. And actually, here is what you can do. So if you apply the greedy algorithm that works so well in, for the Gilbert-Warshamov problem, then this gives you almost everything. So it's just a squared factor. It's a polynomial factor less than everything. And this is very close to optimum. For n odd, you can show that the largest cardinality of such a set where the union of any two contains an even cycle, is not more than this. Well, for even n, we would only have an 8 here. So we could not completely solve this problem. But here, it is reasonable to believe that maybe the greedy algorithm gives the optimum. But I somehow have some hope to be able to completely solve this problem and to understand whether the optimum has a structure. That is the key issue for me that would give lessons to information theory. So when is it that the optimum for a problem, and this is really formally very close to like the co-distance problem. I mean, it has a flavor of information theory, at least to me. So when is it that the optimum has a structure? Or when is it when it is just something that you can get with a greedy algorithm? So I would really be interested in the precise solution of this. And once again, as for odd cycles, also for even cycles, we could ask what happens if you want to have not just an even cycle in the union, but we do want to have a cycle of length 4. Okay? And here we were able to show very recently, so this has not appeared yet, that it makes a difference when you, instead of requiring an even cycle, you require a cycle of length 4. And here is what, what you can see, for instance, is that if you use once again this balanced complete bipartite graph, and then you fix, so you have more or less n-half vertices in both classes, and then you fix, say that n is even, and therefore you can have equality, and now you fix an order in one of the sets, and then you consider all the orders, all the permutations in the other set. And now if you have two different, so in this setup, every permutation of the lower set gives you a Hamilton path. If you decide to start in the upper set and then you alternate between the upper set and the lower set in terms of this prescribed permutation. Now, if you have two different permutations, then as you can see, they differ somewhere, say in the i's value. So sigma of I is here, but tau of I is somewhere else. Then this automatically gives you a 4 cycle. So this is a construction. And what we could prove, and that's really much more complicated, so I won't hint at how we prove it. It's less easy, that the largest cardinality of such a set is significantly less than the number of all permutations of n, half. Okay? So this is the upper bound that we obtained. And this is a paper like, this means as if we were sure that it will appear. Well, we hope that it will, but you never know. Okay? So I'm not sure. I have 6 minutes left, I know, because I use this countdown alarm for teaching purposes. But I was afraid, so I finished a little bit earlier, so maybe you can ask questions. And yes?
Is there an application story behind the difference problem? I wasn't aware of it. It's astonishing.
Yeah, well, like I said, so on the one hand, it's just the capacity, the zero error capacity with feedback, with fixed list size. List size, has a lot to do also with feedback. So of a very specific channel. Well, actually, this was then rediscovered as a perfect hashing problem. And the perfect hashing problem, it has 2 parameters. So you have a B-area alphabet, and you have a fixed block length. I mean, that's one way of presenting it. So you have 2 fixed parameters, B and K. The alphabet size is B, and then you want to use K partitions of the. So you have a fixed set, you want to use K partitions so that any K-table of your elements should be completely separated by at least one of these partitions, so put into different classes. And what is the minimum number of partitions that you need for this? This is just the dual presentation. So rather than fixing block lengths and looking for maximum, here we fix the size and look for the minimum of the block lengths. And so that still is the perfect hashing problem that I guess goes back to Andy Yao, and then I picked it up from Mike Fredman and János, and so, well, there's a history of this problem, and it really interested the computer scientists without them being able to realize. I mean, they would have been able, but they just did not realize, that this was the very same problem, that is a purely information theory problem. And then and then there are other things about this problem, like if you now look at it in a different manner, now you say, I fixed the number of partitions, like I have 2 partitions. And how many K-tuples can I separate by 2 partitions, in the sense that at least one of them would separate these 2. At least one of these 2 would separate your K-tuple, all right? Now, there was this very natural conjecture, which might still be true, that the optimum will be obtained if the joint configuration of your 2 partitions is still an equipartition. Now, the X conjecture of van der Waerden, which is the Falik-Mann-Yegoryshev theorem, says that if the 2 partitions are equipartitions, then the best joint configuration is still an equipartition. But what if they are not equipartitions? Then the answer is not known. And what my result with Scotty Martin that I talked about actually did show that if you have 4 partitions, and you look at how many of your K-tuples you can separate by at least one of them, then the best joint configuration, then if you consider 4 equipartitions, then their best joint configuration is not the equipartition anymore. But it might still be true that even though the joint configuration, the optimal joint configuration is not an equipartition, but the individual partitions going into it are individually equipartitions. Okay, so I don't know whether these are applications. I'm afraid they are not, but but it means that this problem is very naturally and very centrally located in several fields. And I like to use this to say that, well, it's nice to look at problems, in their naked version. Okay. Yes?
You presented results that led to a combinatorial problem.
Yes.
Like, in the version of Gilbert bound, you considered making codes that can correct any number of errors.
Yeah, right.
But, in information theory, the version of Gilbert bound is pessimistic. We can correct more errors if they are random errors.
Yeah, sure.
And, okay, the question is if for a non-combinatorial problem, but still information theoretical, can you use non-greedy or non-random technique, have more structure to get better bounds?
Well, yes and no. Well, first of all, if you look into zero-error problems, that if you buy that as, Shannon theory, which I do, then, well, already this problem that I call difference and the general versions of it show you that even though, we still use random choice at one point, but, what is random choice? I like to say that, well, if you have your optimal construction, then you choose that one with probability 1, and then is that random choice? So there is no rigid barrier, in my view, between random choice and something else. So the more you restrict your random choice to a smaller set in information theory, it's common to restrict it to sequences of some fixed composition, for instance. But here, in this problem of difference, we do something different. And actually, what I consider to be an important application, why this problem of perfect hashing, blah, 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 is important is that it somehow takes the role of Cartesian powers for problems where Cartesian powers won't work. Okay? And this is what we did. So it shows that, so in a way, it does show that random choice is not the solution for everything of information theoretic flavor. And the other example I like from my work with Scotty Martin is the one that I have not presented in detail, because I guess it's more known in this audience, is the modulo to source problem, where again, random choice just dramatically fails. And what is bad about it is that then we are left without even a conjecture of how we should proceed. Okay? Yes?
So your construction for this perfect hashing for 3 or preference,
yes,
it's basically a concatenation code
yeah,
with 9 symbols.
Yeah,
and,
exactly.
It's natural to try to go for more than 9. If you would have a good bound for
5, 6. Yeah, you're right. But like I said, if you are starting with the small optimal constructions and base your concatenation, or whatever you want to call it, on it, the result that you get is not monotonic. So therefore, that makes it less interesting to try, because maybe you arrive with a lot of fatigue to find the optimum for block lengths 5 and 6, and it will turn out that it doesn't give you any improvement. Yeah. If I had many students, I would suggest it to some of them, but yeah. I just gave up on that. For the time being, you never know. Okay?
Let's take all the other questions offline.
Okay.
Thank you very much.
Thank you.